So this is test number 8. This test is mainly based on human eye and optical instruments only, right? Okay, we'll try the first question. The magnitude of an object as seen by the eye depends on, right? So let's draw a human eye. It's a cross section of the human eye. This is the lens, right? Then I can draw axis, let's say principal axis like this. Then if you have an object here, let's say this one, I can draw this light ray coming from this object. So if the object height is capital H and the image height is simple h here, and we have this angle which we call angle of vision. Alpha is called angle of vision. So this is where the eye detects the image, right? So image is formed on the retina. Here you have the retina. So if you have a larger image formed on the retina, you see that object as a larger object, right? So if it H is larger, I mean higher, you see a larger image. So you see that as a larger object. Okay. In order to have this H to be a larger value, this angle of vision has to be larger. Okay. So angle of vision has to be larger. Now you already know the answer for that. So the answer should be third one, right? Height of the image made on the retina. So for that I'll bit explain further. So alpha should be larger. So there are two ways that alpha can be larger. One way is the object can be larger, object height can be larger. Let's say here you have the object. So object is larger, right? So you make a bigger angle of vision, creating a larger image on the retina. Other one is you have to bring the object closer. Let's say you have the same size of the object, but you bring it somewhere here. So still you are making a larger angle of vision. So to have larger images on retina, there are two things you can do. You can bring the object closer, or you can make the object larger, right? Keeping it at the same place. So there are two factors that determines angle of vision. So you just have to increase the size of the, angle of vision. You have to increase the angle of vision. Okay, second question. A normal eye cannot clearly see objects that are closer than 25 centimeters. Closer than 25 centimeters, right? So that is the average distance, the average minimum distance that a human eye can see. So it is about 25 centimeters. If you bring the objects closer than that, the objects start to get blurred, right? Right? So it is about 25 centimeters. So we call that least distinct vision, right? Least distance of distinct vision. That 25 centimeters is called that distance, right? The reason for that is so you know that in order to clearly see, you have to form the images on the retina, right? In order to see objects, you have to form, let's say the object is here. In order to see that, you have to, eye lens has to form the image on the retina. So this eye lens has the ability to change its focal length. So it does form the image on the retina by changing the focal length, right? Focal length. So what happens is, if you are bringing this object closer to the eye, let's say here, if you bring it here, the image I can draw the ray diagram for that case. Bring it here. The image tends to make at back of the retina. So what does the eye lens do? It decreases its focal length in order to take the image back onto the retina, right? Then it fixes. But there's a minimum value focal length can be decreased, right? It cannot be decreased to 0. So that minimum value, there's a minimum value for that. So it has a minimum value, meaning there's a minimum range, minimum distance that the object should be placed. That distance is 25 centimeters, right? So if you further bring the object closer to the eye, if you further bring the object closer to the eye, what happens is it forms an image at the back of the retina, right? At the back. So you would see a blurred image of that object. Already there. So the reason should be there's a limit to decrease the focal length of eye lens, right? So that's the reason. So fourth answer for second question. Right. Third question. When a person with short-sightedness observes an object at far, real image formed by lens. So the person has a short-sightedness. Short-sightedness means the person can see at 25 centimeters. Person can see close objects clearly. The person cannot clearly see objects at infinity. Far objects cannot be seen clearly, right? So what they ask is real image. So what happens? Let's say the object is at infinity. Object is at infinity. What happens is image is formed in front of the retina like this. Okay. So this is an eye which has short-sightedness. Short-sightedness. As you can see, the final image is not made on the retina, right? So I'll explain long-sightedness. So the answer should be is in front of the first one, right? Then for the long-sightedness means person can see objects at infinity but cannot see objects closer. So if we see say object at 25 centimeters, what happens is rays comes like that, and those rays focuses behind the retina. Behind the retina. Again, it is not focused onto the retina. Okay, so this is long-sightedness, this is short-sightedness. You need to remember how to draw these diagrams, and you have to understand it as well, right? So the answer for the third question should be first one. Right, fourth question. A person cannot clearly see objects that are more than distance 250 centimeters. Focal length and type of lens required to prevent the defect is, right? So in this question, what they say is the maximum distance that the person can see is at 250 centimeters. So the problem is he needs to see objects beyond that, right? He needs to see objects at infinity. So he needs to see objects at infinity. But he only can see objects at the maximum length, 250 centimeters. It is about 2.5 meters, right? So what they ask is the lens that should be where. So when you get a question like this, the first thing you have to understand is what should be the purpose of the lens, additional lens. So the function of the lens should be to form image of this object at here. So when you form the image here, right? When you form the image here, then the eye can see, right? So you can say 1 over v minus 1 over u equals 1 over f. So image is formed here. It is 250 minus 1 over u. Object is here, infinity, equals 1 over f. So 1 over infinity is 0. 1 over 250 equals 1 over f. So f is equal to 250 centimeters. It's a plus. So when you get a positive value, it should be a concave lens, right? So you need a concave lens in front of the eye like this in order to prevent this defect. So again, you have to think about the function of the lens. The function of the lens should be the purpose of wearing this lens is in order to see objects at infinity. Eye cannot see objects at infinity. So you need to wear a lens. So the lens forms images of that objects at 250 centimeters. Images of objects that are at infinity is made on at a distance 250 centimeters. So that's what this lens do, right? So you can clearly understand after that what is the image distance, what is the object distance. So the object distance is this one, this is the image distance, right? Then you can use lens equation to find the focal length. Okay, so the answer should be second one, right? For the fourth question. Right. Then the fifth question, power of lens worn by prevent short-sightedness minus 2.5D when he's not wearing lens, far point of his. So he has a short-sightedness. Short-sightedness means he can see near objects, he can't see far objects, right? So first, let's find the focal length of the lens. So we have this equation P equals minus 1 over f. So P is minus 2.5, 1 over f. So minus minus cancels off, then f is equal to 2.5 meters. Meters means in order to convert into centimeters, you can multiply by 100. So you get 250 centimeters as the focal length. It is a positive value, so it is clear that this should be a concave lens, right? So it should be a concave lens. So what they ask is far point. Far point means the maximum distance that naked eye can see, right? Meaning it is the furthest point. For a healthy eye, furthest point is infinity. But for an eye with defects, furthest point is less than infinity. Okay, so we now find this one. Let's draw an eye to clarify this. Again, think about the purpose of this lens. Purpose. So if you have a far point, this is the furthest point he can see. So objects at infinity is made on the far point. This is the far point. That is what the lens do. So here you have the image. So if you find the image distance, you get the If you find the image distance, you get the distance to the far point, right? So this is 1 over v, 1 over u equals 1 over f. Okay. So we have to find v, right? U is infinity, object is at infinity. F is 25 centimeters. Then you know 1 over infinity is 0. Then you can flip this both sides, then you can get 25 centimeters as the image distance. So this is where the distance to the far point, right? So the answer should be second one for fifth question. 25 centimeters. Sorry. It is 250, right? 250. So it should be 250 centimeters. 250 centimeters. That is 2.5 meters. So the answer should be fourth one, right? Answer should be fourth one. Right, 6. If a person cannot clearly see objects that are less than 100 centimeter in distance, power of lens required to clearly see objects at 25 centimeters is. So a normal eye can see objects at 25 centimeters, right? Normal eye can see objects at 25 centimeters, but this eye can only see objects at 100 centimeters. But if you need to read a book or something, he cannot, right? Because the closest he can see is 100 centimeters. But he needs to see objects at 25 centimeters. So he needs a lens. So the purpose of the lens should be objects. So he needs to see objects at 25 centimeters, right? But he only can see, this is a far point of him. Sorry, near point of him. So he only can see objects at 100 centimeters. That's the closest point to him. So the lens, he needs to wear a lens. So that lens has to make images at 100 centimeters. So once the lens forms image at 100 centimeter of objects that are at 25 centimeters, then the eye can see, right? So this should be the image distance, this should be the object distance. In order to find the lens, just apply lens equation. So V is 1 over 100, right? Minus 1 over U is 25. 1 over F. So notice these values are positive values. Why is that? The light is coming from this side, right? So the measurements are taken to the opposite side. So if the measurements are taken to that side, according to sign convention, these values are positive, right? Okay. So this is 100, 1 minus, you have to multiply by 4, 1 over F, minus 3 over 100. So the focal length should be minus 100 over 3. 100 over 3. Okay. They are asking about power, right? So in order to find power, you need this equation. So you put 100 here if the focal lengths are given in centimeters, right? Then it is easier. If it is given in meters, it is minus 1 over F. If it is centimeters, you can at once convert that into diopters. So minus 100. So focal length is in centimeters. So 100 divided by 3. So we have minus here, minus minus plus. 100 cancels off, 3 goes up, 3 diopters. Get it? So the power of the lens is plus 3 diopters. The answer is third one. Okay. Okay, seventh question. A person has a near point at 50 centimeters and far point at 150 centimeters. If he needs to correct the defects, power of the lens is required, right? So he has defects. So he has both short-sightedness and long-sightedness, right? First, we'll think about 50 centimeters. Near point is 50 centimeters. So he needs to fix that to 25 centimeters, right? So this is the near point, 50 centimeters. This point he can see. He can see objects at 50 centimeters. But he needs to fix that. So he needs to see objects at 25 centimeters. So for that you need a lens, an additional lens. So the purpose of the lens, function of the lens should be, it has to create images of objects at 25 centimeters at 50 centimeters. Okay. So now you know the object and image. So you know object distance and image distance. Just apply lens equation. I'm applying this to this lens, right? Not the eye lens. Okay, so image distance is 50 centimeters. Minus u is 25 centimeters. 1 over f. 50, 1 minus 2. So f is minus 1 divided by 50, that is minus 50 centimeters. So this is the lens we require. If it is minus, meaning that this lens is a convex lens, right? So you need a minus 50, but you need power. Since the focal length is in centimeters, I am using this equation. Minus 100 divided by minus 50. So you get minus minus becomes plus 2 diopters. So that's the lens for in order to prevent short-sightedness, long-sightedness, but he has both, right? Then the far point, this is the near point of him. Then you have the far point. Far point is not infinity, it is 150. Far point is 150. Okay. He needs to fix that to infinity, meaning he needs to see objects at infinity. So let's say this is infinity. So you need to wear a lens here, right? The lens, the function of the lens should be objects at infinity should be made on far point of him. Image should be made on the far point. So let's apply this equation. So here you have the image. This is the image distance. Object is at infinity. Object distance infinity, 1 over f. So this value is 0. You can flip this. F is equal to 150 centimeters. Then you need to find power minus 100 over f minus 100 over, this is 150. Cancel off 2, 3 minus 2d over 3. So this is the power of the lens. That is, so you need two lenses. You might have seen in spectacles, right? There are two lenses. At above there's a lens and below that there's a lens. So you need, if you're suffering with both long-sightedness, short-sightedness, you need to have two lenses at the same glass. So here you have a plus 2d minus 2d over 3 diopters. So the answer should be, I think, first one, right? Seventh, first one. Right, then we'll move on to the 8th question. A convex lens of focal length 5 centimeters is used as a simple microscope. Minimum and maximum angular magnification of it is, right? So minimum angular magnification of a simple microscope is D over F over FV. Maximum angular magnification, you just have to add a 1 there. You need to remember these equations, right? I'm not going to prove these two, but you need to be able to prove these as well, right? So this is D means least distance of distinct vision, that is 25 centimeters. F is 5, so this is 5. You are not substituted minus C, right? Because these are magnifications. You just need to get the how many times something is larger. So you don't need negative values there. So this is 5. Then here 25 over 5 plus 1. So it should be 6. So this is the maximum angular magnification. This is the minimum angular magnification of a simple microscope, given that focal length is 5 centimeter. So the simple microscope has only one lens, right? Only one lens. So the answer should be second one for that. Okay, then 9th question. To get maximum angular magnification from a simple microscope is still a simple microscope. Object should be placed slightly beyond focus. So as you saw that earlier, for maximum one, you get this equation, right? So when we are proving this one, we have to make sure the final image is made at D distance, that is least distance of distinct vision, that is 25 centimeters. So the image should be made at 25 centimeters in order to get the maximum angular magnification. So you need to form the final image at 25 centimeters, right? You can recall the theory notes. So the answer should be 5th one for that, right? I'm not going to prove that. So that is the fundamental requirement there. The final image should be made at 25 centimeters. So that is the closest point that the eye can clearly see, right? Right, 10th question. Angular magnification of a compound microscope in normal adjustment is 30. Linear magnification made by objective lens is. Then what they ask is linear magnification of eyepiece. You need to remember this equation as well. M is equal to M naught times ME. So this is linear magnification by the objective lens. This is linear magnification by eyepiece. So if you multiply both, you get the angular magnification of this compound microscope, right? Compound microscope has 2 lenses, right? If you remember. So what they say is at the normal adjustment, angular magnification is 30. An objective lens has a 6. You need to get linear magnification of eyepiece. So that is 30 divided by 6, it should be 5, right? So the answer is third one. So you just have to apply these equations. You need to remember these equations, right? They won't give you these equations in exam. So you need to remember this. Okay. Right, 11th one. To get a larger angular magnification from a compound microscope, so you need to have a larger angular magnification. Capital M should be larger. So what they ask is what should be the lenses in order for that to happen. if you remember this equation, this question is going to be easy. -1, 1 plus d over Fe. So this is linear magnification of objective lens. This is for the eyepiece. So if you observe this one, f0 has to be smaller. Fe also has to be smaller. So in total, it will contribute for the angular magnification to be larger. So this at denominator, right? Stuff at denominator has to be smaller. So the whole thing gets larger, right? Here this thing is f0 and Fe should be smaller. So the both objective lens and eyepiece should be less. 11th one, that is third, right? So to get an answer for this, so if you don't remember the equation, it is a bit hard to get the answer there, right? So it is better to remember this equation as well. Sometimes they might ask, you don't have time to prove this, right? So it's better to remember this one as well. Right, 12th question. When eyepiece of a telescope with least angular magnification capital M is replaced by a lens of half the focal length, its angular magnification is. So for this one also you need to remember the angular magnification. Least angular magnification, right? So for a telescope, we prove angular magnification is f0 over Fe. Least, this is the minimum angular magnification. So it is f0 over Fe, not Fe over f0, right? It is f0 over Fe. So let's say you have this telescope. So you can always remember, normally you look above from a telescope, right? You observe objects like this. So you can see f0 is above, Fe is below, right? Like that you can remember this equation. Don't mix this. Many times they have asked questions from this alone. So what they say, eyepiece, right? Eyepiece is replaced by half. So you have to multiply this by a factor of half. So this is halved. Something at the denominator is halved. So this half goes to the numerator, it becomes 2, right? So it's obviously should be 2m. f0 does not change, but you take eyepiece, focal length of the eyepiece halved. So whole thing gets doubled, right? Because this is at the denominator. So the answer should be fourth one. You should be able to do stuff like this, right? Without writing too many equations. Okay. Then 13th question. Focal lengths of a telescope are 100 centimeters, 2 centimeters. Angle of vision of moon on naked eye is 0.5. When moon is observed through telescope at normal adjustment, remember normal adjustment in a telescope. So for a telescope, what is normal is, whether it is a normal or a not normal adjustment is dependent on where you make the final image, right? So normally you see objects at far away, you observe objects, far away objects at infinity using telescopes, right? So what is normal for a telescope is the image also should be made at infinity. That is normal for the telescope. So for a microscope, both simple and compound microscopes, the image should be made at capital D distance. That is least distance of distinct vision, right? That is where you need to form the image, D. That is normal for microscopes. But what is normal for telescopes is making images at infinity, right? So the equation for that is F naught over Fe. This is angular magnification. So angular magnification also is equal to alpha dash divided by alpha. This alpha is when you see the object with naked eye. This alpha dash is when you see the object, angle of vision when you see the object through the telescope. So here what they ask is alpha dash. Okay, just now you just have to substitute values. F naught is 100, F is 2. Alpha dash divided by alpha is 0.5 degrees. So 100 divided by 2, it is 50. 50 times 0.5 degrees. So this should be 25 degrees. So this is the angle of vision. When you observe the object through the telescope, right? So it has increased by 50 folds, right? So that is 25 degrees. Got it? So if you remember this, you just have to remember these equations, right? And you should be able to prove these as well. So if you remember, in order to answer for MCQs, you must remember these equations. I mean, in light, there are many equations, many stuff that you have to remember. So if you remember, then it is going to be easy. These are simple questions. Okay. Right. Then 14th question. When a telescope with eyepiece which has a focal length 5 centimeters. Okay, I'll just draw a telescope, cross section of a telescope. So eyepiece has a focal length 5 centimeters. This is the eyepiece. In normal adjustment. Then they have given the distance between the objective lens and eyepiece, that is 20 centimeters. So what they ask is eye ring. So let's say eye ring is here. So what is eye ring? Eye ring. So you know, when you observe objects, usually when you observe objects at like in the space, right, using a telescope. So the light coming from those objects is like very small amount of light comes from those objects. Okay. So that light is like, because those are very far away objects. So in those cases, it is better to place the eye at an optimal position. So all the light coming from that after going through the telescope would enter the eye if you place the eye at the eye ring. So for that you need to find eye ring, right? There's an easier way to find the eye ring. The thing is, you need to think that objective lens as the object. So this is the object distance. Then using this one, eyepiece forms an image of the objective distance at the eye ring. So this is V. Then you can just find V. That is the position where the eye ring is. So to find that, you need this lens equation. So you are applying lens equation to the eyepiece, right? Treat objective lens as object. Got it? That's all. Then the image is formed at the eye ring. You need to remember that, right? So that is the optimal position to place the eye. Okay, so 1 over V minus U object is, so the light is coming from here. So it is measured to this side, so U should be 20 centimeters. This is a convex lens, so the focal length should be minus. So 1 over v equals 1 over 20 minus 1 over 5. Take the denominator, 1 minus, this is 4. So you get minus 3 over 20. Okay. Then flip, v equals minus 20 over 3 centimeters. V equals minus 20 over 3 centimeters. Okay. So the answer should be fourth one. So that is where you need to place the eye in order to have the maximum amount of light coming through the telescope. Right. Then we'll try a 15th one. As shown by the image, two arrows are printed on a paper. When it is observed through a telescope, image that can be seen is right. So let's say this is the telescope. So you are observing objects, parallel rays coming from infinity, and inside it you can draw ray diagrams, and if at the normal adjustment the rays coming out also is parallel. As you can see, these are double arrows, double arrows, double arrows. So if you have an object like this, image is flipped, right? That is emerges from the telescope. As so you are placing the eye here. So this flipping of the image causes horizontally and vertically, right? Horizontally and vertically. So you have two arrows like this. So just flip this either horizontally or vertically first. So I'll first flip around horizontal axis. Got it? So this goes here, this goes here. Then flip vertically. Vertically. So this arrow towards the other side, this arrow towards this side. Okay. So this is what you would see when observed through a telescope of this one. You need to remember these are 3D images. I mean 3D, this happens even though we draw only a cross section, that happens to the horizontal direction as well, right? So the answer for that should be fifth one, for the 15th question.